going to speak about stateless Ethereum. When we talk about the state in Ethereum, what we mean is the set of all accounts, of all balances, of all data that belongs to an account. So your wallet balance, your USDC balance, all those things, all the CryptoKitties, all the NFTs, everything. And so the state is what makes Ethereum special, of course. That's what gives Ethereum an edge over Bitcoin, for example. But the problem is that the state is growing. So we have, if you go to this page, which is called the lab, I forgot to give the link, but it's lab.ethpenaops.io. You have a lot of graphs such as this one. And you can see the state grows, and it's not exactly an exponential, but it's starting to look like one. So yeah, this is a bit of a problem. The state is about 217 gigabytes today, and I'm extrapolating with the last over the last year. Of course, it used to be less than this, but you can see this little thing here. That's 50 gigabytes per year, so it grows fast, and it becomes a problem simply because all that state is stored in a database, and the performance of a database is going to crater as the state grows bigger and bigger. And right now it's okay, you don't really see it. In fact, you might get the impression Ethereum is going faster and faster. But there will be a point, and unfortunately it's going to be to come as a shock. It's going to happen in just from one moment to the next. The data will be such that the performance is going to crater. We know that because we tested, and we found out about this problem. So the perfect solution would be to not to use a database. Don't store anything in the database. So what we do is have the idea of self-contained block. You have the block, you receive the block, but you also receive the part of the state that you need to verify, to execute this block, to do whatever you want, but at least you got the right context. And this extra data is called a witness, so it's all the accounts that you access during this block, all the proof that some things that get created, when something gets created, there was nothing before, things like this. So the advantage is that if you can achieve that, this is great, because you don't really need to do a sync. If anybody is running a node, they might know how long it takes to get the state. Well, we want to get rid of that, so that would be a very sweet spot to be at. So how do we get there? Well, let's look first where we are today. And the state currently is stored in what we call Merkle-Patricia tree, or MPT. An MPT is a tree that has what's called an arity of 16, which means that every node has up to 16 children. And so each node, for example, this one has 15 siblings. And then you go on the next level, and so on and so on. So this is, of course, a representation that is a bit simplified. The tree is much larger, 270 gigabytes total. But what you can see, if you want to create a proof, you have to pass all 15 siblings at every level, and this adds up. So you end up at having about 4 kilobytes, give or take a few things, just to prove the inclusion of one value. In a block, you access maybe 1,000 values, so this can balloon fast. To make things worse, smart contracts, they have code. You know, they're programs, they have code, and that code is only referred as the hash of the entire code, and that means that if you want to pass this in a witness, if you want to pass this to any node that does not have the state, you need to pass the code, and the code really comes as a slab, as a big chunk, which means you can actually craft blocks that are extremely pathological, where the block would be 330 megabytes, like the witness would be 330 megabytes. Now, imagine if you produce a block Oh, and by the way, that was those are numbers from before we increased the gas limit from 30 million to 60 million. So now it's more like a half a gigabyte. And imagine you produce a block. You have a lot of nodes on the network that try to replicate your block. You have to send that witness to them. That means you have to send half a gigabyte. Let's say you have 20 peers. Half a gigabyte to everybody in less than 12 seconds. And then they need to connect to their own peers and send it over. So that's a lot of data, and that means you will not be able to achieve that. If such a pathological block happens, the block is missed, basically. Oh, and one thing I forgot to say is this 330 megabyte block is very cheap to do because of the way the code is stored. Yes, you can, for $25, you can create a block like that. Yeah, that's going to kill a lot of things on the network. So we don't want that, obviously. We would also, because by the way, 24 kilobytes is the maximum size of a code, of a byte code. There's a reason why there's a limit. In fact, there are several reasons why this is the limit. We would like to expand it because everything that is really interesting requires more logic, so more data, more code. But if we do this, we paint ourselves in a corner, because that means the future witnesses will be even larger. So what we suggest is to replace the tree with a binary tree. And you can see each tree, at each level, a tree has two siblings. So you do have more nodes, right? The depth is higher. But because you only pass one sibling instead of 15, you actually reduce the proof size by, the witness size by 4x. So it goes from 4 kilobytes to only 1 kilobyte. On top of that, what we want to do is chunk the code in pieces, and instead of referring the code to the code as a whole, we just refer to one piece at a time. Every time we use it, we add it to the witness, but just the piece, not the whole code, which is great because that means we can then expand the size of the code. And yeah, you will have to if you don't access most of it, you don't have a problem. And so the worst case, if we do all of that, is 10 megabyte witness, and that's a lot more practical. This is still a bit heavy if you have to send it to 20 peers and 5,000 validators overall on the network, but it's much more realistic. Now I'm going to detail a bit code chunking, which is what I was referring to before. We want to cut the code into smaller pieces, and in fact this is the more interesting, the more explanatory view. Imagine your code is 23 chunks, but when you start the code, you can jump here, which by the way is incorrect. You should always jump, like it always starts at the first, but okay, that's besides the point here. So you start executing this, and then you jump here, and then you decide to jump here. Why not? And then you come back here and you exit. So you can see there are more codes, parts of the code that you did not touch than those you touched. So in the current model, you have to pass it all. It's a slab. Here, you just pass what you use. So it's smaller. And of course, that's not the end of the story. We also associate a gas cost to every time a chunk is being accessed for the first time. So that means if you want to execute the whole thing, you can, but it's going to cost you more money. So it matches between the usage and the size of the witness, which is something that did not exist until now. Mind you, this is not only for witnesses, it's also for executing code in memory. So if we want to have code that is, 100 megabytes in the future, why not? Geth, for example, is, I checked this morning, is 77 megabytes. So if you want something complex that will take more code, but you don't necessarily want to load everything into memory, especially if you want to do execute contracts in parallel, if you want to do a lot of things. So with this approach, you can just load everything as you need it, one by one. you pay for it. So every time there's a load, there's a gas cost associated to it. And so it's a much more, I would say, future-proof model. Like I said, to do this, we're going to change the gas cost. It's going to become a bit more expensive. And the reason for this is because we are putting the code inside the tree, so we treat the code like any other part of the state. Like code and data are exactly the same thing, and so they are treated the same. So since they are treated the same, you should pay the same. So far, you get a huge discount on using code, and we have to fix that. It's a bit sad for applications because it's going to become more expensive, like I think 20% in our estimates. But the result is that we have something that is more perennial, because we don't ask anybody on the network to subsidize execution for everybody else. So quick recap in terms of clients. Today we have stateful clients. You need over 1 terabyte of space on your disk. It's actually less true today because you can delete the block history, but the idea remains the same. It takes hours up to days to synchronize, to get in sync with the network. You need powerful-ish hardware. I mean, we say 32 gigs of RAM, a processor from 5 years ago, and then NVMe. You know, it's a bit expensive. You know, it's going to be 1,000, 1.5 thousand euros. But yeah, it's still manageable, but it's quite it's something you need to buy and maintain. And then the future, potentially, stateless clients. So you store just what you need and nothing more. You get an almost instant synchronization, because the proof to execute a block is correct. If you know that the block is the head of the chain, then you know the block is correct. You're exactly where you want. You can run it on the phone, potentially, on the browser. The joke, the meme, is that you can run it on a watch. I'm not sure why you would, but in theory it's possible. Justin Drake loves this watch meme. And then, yeah, it's like a light client, but you don't need to trust anybody, so that's pretty great. And you can still be a validator. So I don't know if you have people validating, creating blocks here today, but if you experience this is a lot of trouble. You need the machine. You need to make sure it doesn't, you need to have a contingency plan if you're on holiday and the power is cut off. It's a lot of headaches. I mean, in fact, most people I know just say, well, if it dies while I'm on holiday, I'll just turn it back on in 2 weeks. But yeah, that's the kind of thing. Whereas in this new model, all you need to do is you can run it on a Raspberry Pi, potentially, plug it and forget it, and it's not going to bother you too much. So what do we get out of this? We get a lot more transaction per second. Like I said at the start, the problem is the DB. If every validator on the network does not need to maintain the state in this DB, they can re-execute faster, which means you can give more time to the block builder to produce the block, and because you know that when the block is created and propagated, it will be much faster to verify. So you can put more transactions inside a block. Better decentralization, so it depends on the model. It's definitely better for the validator. In some models, it's also good for the builder. Yeah, I was talking about trustless like client, but more importantly, and I'm going to talk about this, it enables state expiry. And then, because the proofs are smaller, it facilitates interoperability between L2s, between L1 and L2. So if you looked into native rollups, for example, that's a great unlock. All right, how do we switch from the current tree to the new tree? There's about 1.5 billion accounts in the state. You're not going to be able to convert that in 1 second, like in 12 seconds between two blocks. It's just too long. So there are several ideas that have been proposed. There's one that I haven't mentioned this, but I'm going to mention. I haven't mentioned it on the slide, but it's called the Roll-Up Appreciation Week, where we just turn off the chain, translate, and go back the next day hoping everything is translated and correct. That's of course like a straw man, we're not going to do that, but at least that gives a reference point in what we want and what we don't. There's something a bit similar. We keep running the chain, but we just do the offline conversion offline. This has several problems, so we haven't really created any IP for this because we tried to look into this and it was so complicated. Then we said we're not going to do this. The reason for that is you need twice the space on your disk during the conversion. You need to store 2 trees, and once the conversion is done, the chain has progressed. So you need to replay the blocks in that alternative history. And this is very risky to do because there might be something that was correct in the old way of doing things that might not be correct in the new way of doing things, and you will only find out when you replay the blocks, so you can find yourself stuck. Excuse me. It's a bit dangerous. So what we want to do is the overlay transition. And how does that work? Before a transition, you just have a Merkle-Patricia tree with 3 accounts. So if you want to read the account B, for example, you go straight to the MPT. You want to write, same thing. And then the transition starts. So we create a transition period. And we put another tree on top, which is the target tree, the binary tree. And we call the overlay. And then the MPT is frozen, so you can no longer write to it. You can still read from it, but you cannot write to it. And if you want to read from an account A prime, that is actually an updated version of account A. So, for example, you transfer some funds to it, so you wrote, it's here, so you read, you find it in the tree, that's good enough. That's the end of your read. If you want to read an account that is not currently in the overlay, you continue and you read into the MPT, you find it there, you return. All the writes, because this tree is frozen, so all the writes will end up in the MPT. So a new account D here has been created that will mask any potential account D that existed, even though in that case it didn't. And then, and that's not really well represented, so I need to improve this slide, but you have an iterator that goes over the state, and the stride of that iterator is like 10,000. So every block we convert 10,000 accounts, 10,000 slots, and those things are copied into the bin tree, into the binary tree. So that means that when the iterator sweep has ended, all the data that were not clobbered by the overlay tree have been copied into the overlay tree. So all your data has been converted. That's the TLDR. And so you no longer need the MPT. You can delete it. One important point is that once account A once account A prime is clobbering account A, I can delete account A. So I don't have to store both trees on the disk. So it's saving space. It's putting everything in consensus, so we know if something is wrong, we can just use the regular reorg logic to fix it. Yeah, so that's what we're going to deliver. And now I'm a bit over time. I'm sorry, but that's not. I don't have to yap too much longer. I want to talk about state expiry. So what you have to know is that the expiry, the state, most of it is completely, most of it is completely dead. Some people, they create a contract, they store some data, they never touch it again. We don't necessarily know why. We have some intuition. For example, we know a lot of things are related to MEV. But if you're doing MEV and you're trying to collect a lot of money from some other transactions, the thing is, if you create a contract, you're not going to care about cleaning after you. You spent money to create the contract, but you're leaving it where it is. It's going to cost you money to delete it. So why would you? You don't. So the result is that, like I said, 80% of the data hasn't been touched in over 6 months. And you can see this is pretty much the same line as the one I showed at the beginning. This is the growth of the state. And this is what you do, this is what you get if you delete data that hasn't been touched in, I think this is 2 years, yeah, 2 years, 1 month. What you can see compared to this, like I said, this is more or less exponential. This is more or less flat. I mean, sure, there's a little bump here, but overall you can see it's more or less flat. So that means that you can, if you delete all that stuff that is essentially useless, the result is that your performance remains the same because your database size is the same. And yeah, you can see here, I think if you delete after 1 year, after 6 months, you get 80% of the state. If you keep for 2 years, it's more like 60%, but it's still half your data. And I think people, people might think, well, but deleting data, isn't that against the ethos of blockchain? And the answer is yes and no. Because there are two things. When we started Ethereum, we created, we made a bit of a mistake. We conflated two things. There's the commitment to the data. So you commit that this data was there, and you can prove at any time that it was there. And then there's the storage aspect of it, where the data is stored. But then if you think about it, that means that you can store any data you want. Even if it costs you 100 euros to store that data, it's effectively free, because over time, everybody is expected to store your data for you, and you paid once. Okay, it was expensive, 100 euros, but divided by infinity, that's still effectively zero. So there are two promises that were made together, and I think we still want the commitment. So what we want to be able to do is to say, yeah, okay, you commit your data at this point, like you store it. We ask everybody to store it for like 6 months. So if you need to access it in the next 6 months, no problem. But then we're going to delete it, but we're keeping the commitment to it. So if you provide us with the right proof that this was here at this time, for example, we'll resurrect it for you. And so, yeah, this is, in my view, the distinction that should have been done. So this approach I just described preserves the ethos of proving that something was on the blockchain at some point, but it doesn't promise that things will be stored forever, because then things accumulate forever. And then in 100 years, hopefully Ethereum still exists in 100 years, people will still be storing everybody's CryptoKitties when no one cares about it. This being said, I was surprised to check people are still using CryptoKitties quite a lot. Right, there was something else I wanted to say about that. Okay, that's I'm a bit over time, so I'll skip. So yeah, next question is who's going to hold the state? That's a much harder question, simply because when everybody is expected to store everybody else's data, there's a clear role defined. But as soon as people are free to start deleting data from their disks, the question becomes, who's responsible for this? So this is still an open question. We have the beginning of an answer for this. It's probably going to be wallets and RPC providers, simply because, especially wallets, they make their money. I discovered recently that builders are actually not the one making money, because all the money they earn, most of it, they pay wallets to send them transactions. So actually they are not the ones storing the data. But wallets are the best candidates to store that data, simply because, well, first, they want users to use their services, so they will make sure that in terms of UX, that's better for wallets to provide it. And then they can also charge a small fee for resurrecting. Like, they can charge the user. They can say, well, look, you haven't used your data in 10 years. In 100 years, your grandpa hasn't touched that data in 100 years. Just pay us a little bit. We've been keeping it for you all this time. Just give us a little bit. We'll build a witness for you to resurrect your data, and we'll do it. And everybody's happy. So yeah, this is probably how we answer that question, but this is still very much open. So as a way to conclude. you might have seen recently, and I'm sorry, the picture is really unreadable, but that's because there's a lot of things. Justin Drake recently published the straw map, or the strawman roadmap. You can find it at strawmap.org. And there's a lot of things to do. But what I wanted to point out is that you have binary trees, so about end of 2027. So this is the first step. And then there's another thing that's I can't even read anymore. Endgame state, that's what they call it. Endgame state, which is a solution that probably includes state expiry and potentially other things. So that's more like for early 2029, if the roadmap is on time. Yeah, takeaway. Stateless Ethereum is going to help increase the scalability of Ethereum. If you have any question or if you want to learn more, there are two things. You can go, it's pretty hard to read, but you can go to stateless.fyi, which is the website where we store all our resources. So we have presentations, we have explanations, we have plenty of things for anybody interested. And the second thing is that we are organizing a Stateless Summit in Cannes during ETHCC on April 1st, not a joke. And if you want to participate, you are welcome to. If you want to learn, if you want to contribute, please, this is our landing page, so please come meet us. And that's it. Thank you. Yeah, go. Oh, sure. Yeah. No.
Why the state expiry method was chosen, contrary to the rent of the state?
The honest answer is I don't know. I haven't figured it out myself, but the more serious explanation would be that people have tried. It's a very difficult UX problem. I've heard about state rent since 2018. I haven't seen a single, Ligi is shaking his head in approval. This was a concept we've been playing with since 2018. It has never delivered anything palatable. So yeah, we just decided to move on to something else. But if you feel like implementing state rent and you have a solution that satisfies everybody, well, first of all, good job, and second, come talk about it. Yeah, Ben.
So when you mentioned the partitioned contracts, will this be similar to like access lists in your transaction? Like there'll be a new transaction type to say I'm going to access these components as parts of the contract.
Right. So I forgot to repeat the previous question, but are the contract chunking, is it like access list? No, it's completely orthogonal. We are going to. I mean, you could add those chunks to the access list already, so it's not a problem. But yeah, it's really just witness based. So if you want, you can add them to your access list. But this is kind of replacing access lists anyway. So when you can, I mean, I would say the design space is open. But what we want to do is really I would say the cost aspect of it is very much like access list, but the access list would be deprecated. So now. Okay, I was talking about transaction access list. Now there's block access list. So in that case, that would be pretty much the same. So it's a list of locations you access, including code, that would be attached to the block. Sir?
Yeah, so maybe a very naive question, but so I'm wondering about if you want to optimize more for hardware, less hardware requirement and more TPS. And I'm wondering what's your kind of goal or trade-off? Because for example, if you compare it to Solana, which is very centralized because the hardware requirements are so crazy, but then it's also very fast. And I'm just wondering where we should be aiming.
Yeah, okay, so let me summarize this question. Yeah, okay, so do we have a trade-off curve between centralized fast building and decentralized slow building? Is that a fair summary of your question? Yeah, so we still want anyone to spin off a node. So this is definitely, I would say this is non-negotiable. The one thing that is currently up for debate, and I'm going to try to be to give an honest rendition of the other side's argument because of the other side of the debate. Some people want centralized block building with very powerful machines, and the idea is those people will will be like provide the speed that Solana has, and then everybody is still able to verify using stateless proofs. So this is personally not the model I want. So once again, I'm gonna try to sell it. I'm definitely going to make a bad job at it because I don't believe in it, but yeah, like the idea is you can try to do the best of both worlds by building fast and centralized, and verifying. So still keeping the decentralization, because if a centralized actor misbehaves, you can slash him, you can refuse his block. So yeah, that's I mean that's pretty much how rollups work as well. It's centralized block building, and then if they misbehave, you have a chance to claim a fault and refuse that block at the L1 level. Was that a...
Yeah, it's a great answer.
All right. Chris?
So do you have thoughts how decentralized block building could work if the centralized one is...
Yeah, maybe do I have thought on how decentralized block building could work? Yes, I mean, you would not necessarily get the same scale, of course, because centralized block building is always going to be faster, clearly. But the question is, how do you build decentralized block building that is fast enough for the current use case, right? And yeah, there are plenty of things we could do. I mean, we could, for example, work on our database engines instead of pouring all our resources on this approach. So if I go back to the yeah, I'm sorry to to bring this back, but they want to have mandatory proof here. So it's ZK proofs proving this can only be done in a big server. Like the computing power required to achieve this box is you're never gonna have that. Okay, you're not gonna have that in everybody's home in the foreseeable future. So that means only big builders can have that. Well, instead of working on shipping this, we could just rewrite our database engine. It's gonna give us a 3x improvement. It's not as good as what this promises, but at the same time, it's achievable and it can be done in the same time frame. Okay. Oh, Ben.
So this one account that got polluted, your image of the overlay.
Yeah.
A to A prime. Is this more like contracts that are accessed frequently? These accounts are being migrated to the same address, right?
Yes, it's the same address, absolutely.
And this account A prime is unlikely to be an EOA, but rather a
No,
contract.
it's anything. If it's not clear, I can explain offline.